But it's not super loud, right?
Yeah, you didn't even call it that.
Can we force? That is selected, so just picking that up now. Cool. Can you hear us, Adina?
Yeah, I can hear you now. Can you hear me okay?
Can you hear? Good, bad, good. You guys want to go?
Yeah, the audio and video is a little choppy.
I think it's just the internet. Yeah, our internet looks fine, but it's kind of yeah, she's at home. So I think we're done with it. We should be good to go.
Okay. All right. Hello, good morning, everybody. Nice to see you. I have a couple of quick announcements to make before we get started. First, just as a reminder, you need to be masked in class and your mask needs to remain over your nose. And then a couple other just quick announcements in relation to the email that I sent you guys over the weekend. I'm going to do a quick screen share of Moodle just to talk about a couple things. So first is a reminder that our drop-in help starts today. So if you are working on homework or other things related to the class and you need some help, we have a TA help center that is open from 2 to 9. And you can also see the schedule here. It's not completely finalized. There's some movement, but the times will remain the same. So one thing that I will mention is if you go to drop-in help and you find a TA who you really click with, who really helps you, then you can look at the schedule and see when else they're working. I do highly recommend that you schedule your time outside of class to work on homework during the help center hours so that you can drop in and get help whenever you need. So those are there. Those start today. The links are here. This week is a little wonky because Wednesday is going to be a Monday schedule. So the TAs that will be there on Monday, normally on Monday, will be there on Wednesday of this week. So you can keep that in mind. Also, because of the schedule, my office hours are slightly changed for Wednesday because I do have a meeting. But wherever the link doesn't say TA, those are my office hours. So you can see this Wednesday, I'll be there from 9 to 10. A couple of other things. So I did manage to somewhat figure out how to set up a live stream link. I'm testing it out today for the first time. I have a TA watching and someone else watching to see if it works. But again, this is, if you get sick and you have to be at home and you can't come, but you want to watch it in real time, you can use the live stream link during the class period. And I will be streaming the lecture as we go. And then the question document is where you can write questions that are coming up in class. So we're going to try that out today. Hopefully the live stream works and we'll be able to, I'm going to sneeze, I'm sorry. Excuse me. And hopefully we'll get that going from there. I also want to point out that if you get sick and you can't come to class, or if there's a holiday for your religion or something of that sort where you're unable to attend class, all of the lectures that I'm giving are also recorded asynchronously. So I have the lectures from when we were fully remote. So for example, if you had missed class today and we were covering what is a function, underneath the guided notes, there is a was a function link and you can watch the videos there if you need it, or if you just need to brush up on something. So if we cover something in class and you can't quite remember something or you want to go over it again, when you click on that, there's smaller videos you can click on to watch them. So this week, you guys are going to have your first set of mini quizzes. So I want to talk about that for a quick second. So again, on the mini quizzes, these are 15 minutes. There's 3 questions that are multiple choice. And once you click on the mini quiz, you have 15 minutes to complete it. So you can do this in any 15-minute period. You can do it later today. You can do it tomorrow morning, but you have to complete it by tomorrow night at essentially midnight. So in order to do this mini quiz, what I recommend is trying some of the homework first to practice just doing out some of the problems. And then once you feel okay about some of the homework, then you're probably in good shape to do the mini quiz. And I want to point out that one of the main benefits of having a remote year last year was we were able to change the assessment structure of how this works. So these mini quizzes are low stakes. I mentioned this before, but if you don't do well on one of them, there's so many of them. There's 21 of them across a semester for a total of 63 points. So if you don't do well on 1 or 2 of them, it's not going to be a big deal. So we have been able to change the assessment structure from high stakes testing into low stakes testing by having a lot more of them, which is beneficial for everybody overall. So if you are a student who receives extra time, when you log into Moodle, you'll see that this should say 30 minutes to complete it. And that means that you are all set with your extended time. And so the rest of it is stuff that I've gone over before, but you can see the second mini quiz is going to be due on Sunday at midnight. And you can do that after we've covered 1.3, which we'll do on Thursday. The other announcement I want to make in relation to the email I sent you, under getting started, there's the algebra assessment that I asked you guys to look at. If you are feeling like you didn't know how to do a lot of the problems on the algebra assessment, that's what the algebra reviews are going to be this week. There's one on Wednesday and one on Thursday, and those links were in the email that I sent you. Our grad TA William is just going to be going over these algebra problems. So if you need to brush up on algebra, this is a good way to do it. So this might be because it's been a long time since you've seen it, or it might be that there's some gaps in your knowledge. But if you feel like you didn't know how to do a lot of these problems on the algebra assessment, then I would recommend that you try to stop in the workshop if you can this week, just to get all brushed up. So those are the main announcements. Oh, and there's one more. So I had to change one date, you'll notice on the syllabus over the weekend. Our first chapter quiz is going to be on Monday, September 27th. So that's moved back 1 week from where we thought it was going to be originally. So I've updated the syllabus and saved the dates file, but if you had written it down somewhere, it is moved to September 27th, that Monday, instead of the 20th. Okay, so I think that's all of the announcements here. So I'm going to go ahead and switch over, and we're going to pick up where we left off in our 1.1, what is a function, which we were talking about last time. So I'm just going to switch over to the dot cam. And I did get a new dot cam over the weekend. The other one was a little finicky. So hopefully this one works okay. It's got some features in it that hopefully make it a little bit better. The graphs are still giving me some trouble. I did try to graph over them today, but I may switch to show you the graph on a PDF instead of the dot cam if it's becoming problematic. So again, I just want to remind you that for section 1.1, which we are in right now, there's just a lot of little things that have to do with how we talk about math. So there's a lot of little topics that we're just brushing up on so that we can have the vocabulary later to talk about different types of functions. So the next piece we need to talk about is discrete versus continuous functions. The majority of the functions that we look at in this class are continuous because most of the models that we look at are going to come from functions that are continuous. However, there are some cases where we do have discrete situations, and we just want to make sure we understand the difference between the two. So a discrete function is defined that we only have a set of input numbers that can be listed and nothing in between, right? So what that means is that usually comes up in a table form. So when we have data, so we looked at some examples last time, but I will give you, another example. So, the number of kids that, a person has is a discrete function, right? You can have one kid, you can have two kids, you can have three kids. You don't have 1.7 kids, right? That doesn't make sense. So you don't have numbers in between the integers. So that is considered discrete. But things that are taking any value, right, in between the integers all the way, those are considered continuous. So we will actually define continuity.
Gina,
yes.
You broke up. We heard you don't have 0.7 kids, and that was the last thing we heard.
That's true. I don't have 0.7 kids. Right. So with discrete functions, we're talking about the integers, and you don't have values in between. However, with a continuous function, you have a function that you can plug in any value, right? So it makes sense over anything. So time, things that depend on time are typically considered continuous because there's an interval of time smaller and smaller between anything you would look at. So you could have, 1 hour, 2 hours, but you could also have 30 minutes, 30 seconds, half a second, right? So those things tend to be continuous, and those are things that we can plug in any value. So what we want to do is we want to look at just some examples of the 4 types of functions we have and determine if they are continuous or discrete. So we're going to start with the first 2, where we're going to have a formula and a graph. Actually, let's see if we can get all 3 on the screen. I think we can. We'll do the formula, the graph, and the table. So for the interval given, so for the graph, just where you see it, and for the function above, and for the table, I want you to take a minute and jot down whether you think each of these is continuous or discrete based on what you're seeing here. Okay, so take a minute and jot that down. All right, so let's talk about each of these and figure out if they are continuous or discrete. So for our formula, we have x squared minus 2x minus 3. And we're trying to figure out, can we plug in every type of number, right? Fractions, decimals, all those things. When I think about what I can plug into x, I can really plug in anything. I can plug in a 1, I can plug in a 2, I can plug in a half, I can plug in 1.333, I can plug in pi, right? So any number I can think of, if I plug it in, I will get a Y value. So because I can plug in every single possible number and I get an output for every single possible number, this is going to be continuous. Okay. So when we're looking at functions, we are considering, can we plug everything in? And if so, are there any restrictions, which we'll get to in a minute, but that's our continuous function that we have for our formula here. The second is our graph. So you'll notice that along the horizontal axis here, that we have every single possible number between -6.5 and 6.5. So on the interval where we see this graph, it is continuous, because if we were to pick, say, 1.33333, which we could zoom in and find here, there is an output value. There is a Y value there. So for the graph where we see it, this is continuous. Now, we don't know what happens for the rest of the graph, but from what we see, we know that this is continuous. Okay. So then finally, we have a table. So on the table, we see values for independent inputs 0, 2, 4, and 6, right? So we know the outputs for those values. However, we don't know what's happening at 1 or at 0.5 or any of the values in between. So without any other context, this table has to be discrete. Okay, now I'm going to put a little star on this and a little caveat, which we'll talk about in a little bit, that sometimes you'll have a table and it'll say, assume this data comes from a continuous function. And what that means is that there exists data in between the points we have. We just don't know what it is. However, without that stipulation in the setup, then this function will be discrete, because the only things that we know are these 4 values. Okay, so hopefully that makes sense. So let's try one more, which is a word problem. Okay, so I want you to take a minute to read this word problem. Hopefully you can see it, it's big enough, and determine if this is a continuous function that we're talking about in our model or a discrete function that we're talking about in our model. And jot down either a C for continuous or a D for discrete. So take a quick minute. Okay, so as I mentioned before, typically the word problems are going to be the hardest to evaluate. So we start with ones that are a little bit more straightforward and try to figure things out. So as they get harder, it gets easier. So here our function is talking about the cost of ice cream. That's the output, based on the number of toppings T, which is the input. So the question is really, can we plug in anything we want for T? Right? But if we're thinking about the number of toppings, this really only makes sense if your toppings are integer numbers, right? So 1 topping, 2 toppings, 3 toppings, 4 toppings. You can't really order 1.5 toppings, because as soon as you get past 1, you now have 2 toppings. So it doesn't make sense for numbers in between our integers. So in this case, this situation, we have a discrete model, right? Because the values that we can plug in for T are things like 1, 2, 3, 4, 5. So when we talk about continuous and discrete, this is what we're talking about. We're talking about what inputs we can put into our function. And again, I'm not going to ask you to define continuous and discrete on a quiz, right? I'm not going to say write the definition. But when I talk about other functions later and I say this function is continuous or this function is discrete, we want to make sure we're on the same page about what that means. Okay, so that's continuous and discrete. The next set of terminology, again, we're kind of just bumping through different things we talk about in math, are domain and range. So you've probably heard these words before, and depending on when you took algebra, it may have been a while, or you may have seen it more recently, but this is something that comes up a lot, throughout the course in various ways. So we want to be really careful about understanding the domain and range for different types of functions, because that's going to impact some of the work that we do. So the domain of a function is the set of all possible inputs for a function. So what are the numbers that you can plug into the function? Now, this can be defined by the function. There's certain functions that you just can't plug in certain numbers. The sort of typical example of that, right, is 1 over x. So if we have the function 1 over x, I ask you the question, what are you worried about plugging in, right? So if you think about it, the thing that we're worried about plugging in is 0, right? Why are we worried about plugging in 0, right? That's when black holes erupt and people die type of thing. No, it's not quite that dramatic, but we don't want to plug in 0 because it's not defined there. We all know that you can't have a 0 in the denominator. So the function defines the domain in that we know we can't plug in the 0 from the rules we know about the existence of different types of functions. Now, there can also be restrictions on the domain set by the problem. So, you might get to a problem and it says, for values of x between 10 and 20, what is happening? So someone might restrict the domain for you within the set of a problem, and then you're only going to look at the numbers that are called for in the setup. Now, the range is going to be the outputs of the function. So we're thinking about what are the possible outputs for a function, and are there any restrictions on them? So one that we often talk about, right? Now, if we're talking about the function x squared, the domain is all numbers. We can plug in whatever we want to that without issue. But the outputs, right, the things that are going to come out the other side are all going to be non-negative. So they're going to be positive numbers and 0, right? So we get 0 and then all the positive numbers. So the range is restricted because we're not going to get any negative values out if you plug something into x squared. Okay, so we want to work to make sure we can find the domain and range of different types of functions. So we're going to practice this a little bit. So the first one we're going to try is to find the domain and range for the function x squared minus 2x minus 3. So there's a couple different ways you can do this. I did provide a graph space there if you're somebody who likes to graph it, but you don't have to graph it to answer this question. So what I want you to do is I want you to take a minute and think about what the domain will be based on the function. What can you plug in? Is there anything you're worried about? And what the range will be. What kinds of numbers are we going to get out of this function? And as I mentioned, sometimes it helps to look at the graph. So if you have a graphing calculator, you can certainly pull that out and see what this function looks like. You don't have to. You can solve this completely algebraically, but sometimes it helps. So take 2 minutes. See if you can figure out the domain and the range and write that down somewhere in your notes. Feel free to check in with someone next to you to see if they're getting the same things you are. All right, so let's take a look at this. This is a very rough sketch. I just plugged a couple numbers in to try to get a sense of what this would look like. So when we think about the function x squared minus 2x minus 3, there's no red flags that come up for me about what we can plug in. And the way that I usually try to think about this is, can I plug in 0? Can I plug in a negative number? Can I plug in a positive number? And if all of those answers are yes, I then check, is there a denominator? So do I have one function over another one? There's no denominator in this case. And I also check for square roots because we don't want to take a square root of a negative number. So none of those things happen here. So I'm not concerned about anything. And in my quick test, I was able to plug in a lot of different numbers. And so the domain here, we say is all real numbers. And in the next sort of part of this in a minute, we're going to be looking at how we write that mathematically. But for now, we can just say we can plug in anything. The domain is all numbers, right? Now the range is a little more complicated, right? So if we look at our picture, we can see that these y values are going to go up and up and up forever. So we know that in the positive direction, that's going to go off to infinity. However, we can see that there is a lowest output value, right? So that means that when we think about the range, the only numbers that can be in our range are going to be numbers that start at this value and then go up forever. So only numbers above this value. So how do we figure out what that value is, right? So that's one of the benefits of graphing this. If you do this on your graphing calculator, you can calculate the minimum on the calculator. You can trace it. Otherwise, we'll have to go back to algebra when we learned how to find the vertices of a parabola. I don't know if this sounds familiar to you, but if you find the axis of symmetry, right, you're going to have negative b over 2a, which here my a is 1, my b is negative 2. So here I would have 2 over 2 times 1 because it's the opposite of b, and this was negative 2, right? So that gives me an x value of 1 for my vertice. And so to get the y value, I would need to plug 1 into my function. So 1 squared minus 2 times 1 minus 3. So that's going to give me 1 minus 2, which is negative 1, minus 3 equals negative 4. So this bottom number here, the y value, where we reach the lowest value here, it's going to be at the point 1 comma negative 4. So our range is going to be from negative 4 to infinity. Okay, so all the outputs we get are going to go from negative 4 to infinity. So we can't get an output of negative 5, negative 6, anything outside of that range. Now, most people rely on the picture to find these values, which is totally fine. But if you are someone who prefers to do things out algebraically, you will get the same solution. So whichever method is more comfortable for you, that's totally fine. So again, our domain here, all real numbers, our range, -4 to infinity. Now, we want to think about how we write this, right? We don't want to have to write this out as a sentence every single time. So we have two different ways that we use notation to talk about how we talk about domain and range. Okay, so that's what we're going to talk about next. We'll talk about the notation, and then we'll go back to domain and range. Okay, so we're going to talk about notation first for continuous functions, because that's what we're looking at. So there's two different ways we do this, and I'm guessing you've seen this, at some point. So in general, what we're going to be doing is we're going to either use the greater than, less than signs, or we're going to use brackets and open parentheses. So we're going to start with what's called closed interval notation. So closed interval notation means that we can include our endpoints. So if we're talking about a function and we include the endpoints, we use the less than or equal to symbols. Or we can also write this with closed brackets. Now, depending on, when you took algebra, you may not have seen the second notation. So there's this funny looking E type symbol here. And what that says is X is an element of the interval from A to B. Okay. And what that means is it can take on any value between.
Tina, you cut out again. Do you want to just repeat that they might not have seen the bracket?
Yes. So you may not have seen this bracket, and it's a little bit goofy, but what it means is X is an element of the interval A to B. So that means that X can take on any value between A and B, including A and B. So what that means for the last problem we just did, okay, we said our domain was all real numbers. So when we talk about all real numbers, we're going to include infinities in our practice, okay? And we'll look at that in a second in the next notation. Now, sometimes we have continuous functions where we do not include the endpoints. And if we do not include the endpoints, it changes just a little bit. So instead of having less than or equal to, we just have the less than. And for our alternate notation, we are going to use open brackets if we don't include the endpoints. So this is how we're going to write down things like domain and range when we talk about it. And one really important point is that when you have an infinity, you have to use the open notation, okay? Because infinity is a construct and not a number. And so this sort of gets into some more philosophical discussions about math, but you can't just plug infinity into the concept. So that's always considered open notation. So we're going to practice this notation as we continue thinking about domain and range, and then we'll see how that looks. We're going to try it out. So let's try out domain and range on this picture here. Let's see. I feel like you're not going to be able to see the numbers. So let me darken these up. This is 1. This is 2. -1. -2. This is 2, 4, 6. -2. -4. -6. Okay. So for this function, assuming that the entire function is pictured right here, so it doesn't go on forever and ever, it just stops at the ends, I want you to try to write down what the domain and the range will be for this particular function. Okay, and I want you to try it with your notation here. So you can use the less than or equal to, or you can use the brackets, whichever you prefer, but try to jot that down for this particular graph. All right, so let's see some ways we can write this. So let's start with the domain first. Okay, so again, the domain are the X values, the things that we can plug in the independent variable here. And so I notice here that my graph goes from -2 to +2. And the instructions say that this is the entire function. So my domain has to be between -2 and 2. And so the question is, can I plug in -2 and 2? So you see that here, there is a Y value for both 2 and -2, which means I can include my endpoints. So the two ways that I can write this are with my less than or equal signs. So X is between 2 and -2. Or I can write this as X is an element of -2, 2. Okay, these mean the same thing. So if you have a preference of one over the other, that's totally fine for your notes, but you want to make sure that you understand the same thing. So if on a quiz it says it one way or the other, that you know that they mean the same thing. Okay, so that's our domain here. We can plug in all the values between -2 and 2. Now let's talk about the range. So again, the range is the set of outputs here. And if I look at what's going on the top, I notice that the highest value I reach is 4. And on the bottom, the lowest value I reach is -4. So this one doesn't go off to infinity. It's actually capped between 4 and -4. So the way that we're going to write this is -4, because I actually reach that value, is less than or equal to, I'm just going to use f of x here. Sometimes people like to just write in a y because they prefer the y. Okay, but we're going to be between -4 and 4 for the range. Or if we want to use our other notation, you can either use f of x or y is an element of -4 to 4. And again, I'm using the closed brackets because I can include my endpoints. I will say the majority of the time, we're going to be using closed brackets unless we have an infinity. Okay, so that's the domain and the range for this particular function, and that's how we're going to write it out. And again, you can write it in either of the two notations, but you should make sure that you recognize them both. So if you see it one way in a problem, you know that it means the same thing. Okay, so far we've looked at a formula and a graph, which were both continuous. However, we also want to be able to talk about domain and range in situations that are discrete. So we're going to talk about how we're going to write that, which is slightly different by looking at a table. Okay, so I want you to take 1 minute and think about what the domain and range would be for this particular table. So go ahead and you can jot down domain, range, whatever you think the values are, and then we'll talk about how to write it in just a minute. So try out writing down a couple notes and take a guess. If you know the notation, go ahead and do that. All right, so let's start with the domain. So again, the domain is the set of possible inputs. There's nothing in here that says that this function is continuous. If it said, assume the table below is continuous, then we would just need the two endpoints to figure out what our domain is. But here, because it doesn't say that, we assume it's discrete, which means that my possible inputs here are the values that I see along the top row. Remember, these are the inputs into our independent variable, which here is t. So the domain here, we're going to say t is an element of. Now with discrete functions, we tend to use curly brackets, and then we make a list of the inputs that we allow. Okay, so here, t, my independent variable, an element of, so that means it can take on a value of 0, 1, 2, or 3. And again, those come directly from this table in the top row. So that's our domain here. Those are the possible inputs that we can plug in. Similarly, right, our range is the set of outputs, which here we're calling f of t. And these set of outputs are -1, 1, 7, and 17. So those are the only values that we can get as outputs for this function, because our entire function is just these values on the table. So when we have a discrete situation, we use these curly brackets, and then we list the values that are given to us that are reasonable in this situation. Okay. Now we're going to try one. Yes.
Dina, you cut out again. We heard we use these curly brackets, and that was the last thing we heard.
Yes. So we use these curly brackets, and then we list the values that we get from the table for the domain and the range. But there's other situations where we're going to have values that are not a table that come up in word problems. So we want to look at what that might look like and how we determine what these outputs and inputs would look like if they're not given to us in a table. So let's take a look at the next one. Okay, so what I want you to do is I want you to read this problem about the cost of ice cream. It's the same situation we were looking at before. And I want you to think about how we would write the domain and range here, given that this is going to be a discrete function. So we have to figure out what those values are to list. So take 2 minutes, read through the problem, see if you can use the notation to come up with the domain and range, and feel free to check in with someone near you to see if they're getting the same thing. if we can generate these values for our domain and our range. So again, said here, this is going to be a discrete function because the number of toppings can only be integer numbers, right? We talked about that before. So here we have some additional information that the shop offers 10 different toppings, which means that the number of toppings can be at a maximum of 10. So here the number of toppings could be 0. Did you catch that one? Someone could order 0 toppings if they don't like toppings. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's sort of the long way to write this out. As you can imagine, if a store had 100 toppings, you definitely wouldn't want to write out that many numbers. So there is a shorthand for really long lists, which I'll write next to it, where we use ellipses. So we could also write something like 0, 1, 2, ... 10. And what that means is you can see from the first 3 numbers that we're counting by ones, and then we keep going until we get to 10. So if you have a particularly long list, you can write them out, but you could also write down the first 3 and then ... and then the last one. And that tells the reader that you should stop when you get to 10, just so that you know. So that's going to be our domain. We can take on any number from 0 to 10 for the number of toppings. Now this translates directly into our range, which is going to be our cost, right? Because essentially what we're going to do is we're going to say, okay, well, if there's 0 toppings, I'd plug the 0 into the function and my cost would be $5. If I plug in a 1, if I get 1 topping, it'll be $5.25, right? 2 toppings, $5.50, right? And this is where we're gonna do those ellipses because I'm gonna run out of space if I don't. And then I jump to the last one. So the last one is 10. If I plug a 10 into my function, if I get all 10 toppings on my ice cream, which sounds a little insane to me, but perhaps 10 toppings is delicious. That'll be $2.50, right? So the 0.25 times 10 is $2.50. I add that to the $5 and I get $7.50. Okay, so those are the possible outputs for this discrete function. So we can see it's a little bit different than the table because we have to generate them by using the function that's given. But that's the notation we're going to use for discrete functions. Okay, so that is notation for closed intervals and open intervals, continuous functions, discrete functions. And again, this is so you get used to it because later you're going to have problems where you have this domain and range given to you in the problem, and the notation will give you information about the function. Okay, so the next thing we need to talk about is just sort of putting together what a mathematical model means, because all the work that we're doing is so that we can take real world phenomena and apply math rules to it to try to figure out what's happening. In particular, in this class, what we're going to learn is that we want to be able to take real world information and make predictions about future occurrences. That's sort of one of the huge benefits of calculus, is the predictability stuff. So before we can get to that, where we learn how to sort of predict into the future, we have to get comfortable with the idea of what a mathematical model is. So a model is going to be a description of a system using our mathematical notation and using the functions that we've been talking about. So this can be in a graph, it can be an equation, it could be a table, or it could be a word problem / description. And it's meant to represent a real world situation. So what we want to look at here is a model.
Hey, Dina.
Yes.
I think you broke up around, did you say echolocation or I think at the beginning, mathematical model.
Okay.
It started getting really choppy.
Huh. Is the internet being choppy in there? The video on my end is choppy, but I was just curious.
Can you hear me?
Yes. Can you hear me?
I think it's our internet. Yeah, I think you're good now.
Okay.
Maybe not.
Yeah, it's on super slow right now.
Go UMass. Give it another try.
Okay. Can you hear me now?
Can't tell if she's talking or not.
I was talking. I guess I'll just keep talking until you can hear me. Let's see. I wonder what everybody did this weekend. I'm just gonna keep talking until you can hear me. Whoop. Huh? Are you there?
Yeah, we're here.
Oh, can you hear me now?
Yes.
Okay, I feel like the guy from the T-Mobile commercial. Can you hear me now? Okay, let's try it. So a mathematical model is going to
You're
help us.
good.
Okay. A mathematical model is going to help us describe a real-world situation by using one of our 4 types of functions. So a graph, an equation, a table, or a description. And this is particularly helpful in calculus because what we're going to learn later in the course is how to use these models to make predictions about the future. And that's really powerful because this is how we predict weather storms and stock markets and the behavior of certain things like, tumor growth or patterns on an animal, all sorts of things we can predict if we have a good model. So what we want to do is we want to look at a very basic model and then talk about all the things we've been looking at so far as applied to that model. So what I want to do here, for example, 4, is I want you to read this problem and then answer the 3 questions about the things we've just been talking about. So things like, what are the independent and dependent variable? Is the function continuous or discrete? And what is the domain and range for this function? Okay, so read the problem and take 2 or 3 minutes to see if you can answer these 3 questions using the notation we've talked about or the other things we've talked about so far.
I think you're just supposed to answer the questions.
All right, take about 30 more seconds to finish up the part you're working on. All right, Terry, can you hear me now?
Yes.
All right, perfect. So let's take a look at this and see that if we can apply all the things we've learned here. So we have this popcorn vendor at Fenway, and they're selling the popcorn for $6 a bag, right? So R is the revenue in dollars. So that's the amount of money that they're going to take in for one night sales. And here you can see that the model is R equals 6 times P. So 6 comes from that $6. P is going to represent the number of bags of popcorn, and R is the revenue. So here, when we're determining what is the independent and dependent variable, remember that our independent variable is the one that we get to plug things into. We get to control it and decide the number. So here, P is going to be my independent variable because I get to decide how many bags of popcorn I'm buying, or we as a people get to decide how many we're buying. And the dependent variable is R. So revenue and P for popcorn bags. Okay, so again, our independent variable is P and our dependent variable is R. So we're not using X's and Y's here. We're using P's and R's because of the model. So now we need to determine if this function is continuous or discrete. So again, this is a situation where we need to think about the situation itself and what's reasonable. And so if we think about the independent variable, right, of popcorn bags, you can't get 1.5 bags of popcorn. You can get 1 bag, you can get 2 bags, you can get 3 bags, but you can't get the numbers in between. You can't get 1.135 bags of popcorn. So because we don't get to include all the numbers in between, this particular function is discrete. We can only get integer number of bags. So again, that means like 1 bag, 2 bags, 3 bags, 4 bags, 5 bags, right? We can't get stuff in between. So third, we want to talk about how we would represent the domain and range for this function. So the domain of the function has to do with the independent variable. Remember, the independent variable here is P. And because it's discrete, we're using the curly brackets. Now we need to think about where this function starts, right? You can't buy -5 bags of popcorn. That doesn't make sense. But you could buy 0 bags of popcorn. So we start at 0, 1, 2, ... Now, the tricky part of this is that we know there's not infinitely many bags of popcorn, but we also don't know the maximum number of bags of popcorn. So we are just going to put this like this. So this typically means it's going to go off to infinity, but it can also mean that we don't actually know the upper bound, but that we do know that they have to be whole numbers as demonstrated by the first 3 numbers. So we can see how we're counting and we know that it'll continue on from there. So 1, 2, 3, 4, 5, 6, 7, so on and so forth. So our range is going to look a little bit different because again, our range is the outputs, right, that we can get from our number. So the range is the values of our revenue. So if we were to sell 0 bags of popcorn, maybe the game was canceled, maybe people are boycotting popcorn, maybe it's a bad batch, right? But if 0 bags are sold, 6 times 0 is 0. If only 1 bag is sold for the night, right? Then I make $6. 6 times 1 is 6, right? 2 bags, $12, so on and so forth. And we can see that the revenue is going to increase by $6 for every bag sold. So our range is counting by 6s because the way we get those outputs is from 6p, and p had to be integer numbers. So we can write the domain and range of the function like this to represent what will happen over time. Okay, so that's just sort of an example of a mathematical model. We're going to do a lot more with modeling as we get into other chapters, but it's just an introduction of this idea that all a mathematical model is a representation of something that's happening in the real world. Okay. All right. Move this over a little. So one of the things that happens for us in a function is that the intercepts often have real world meaning that are important, right? So these intercepts happen when we cross the 2 different axes. So first is the vertical intercept. The vertical intercept, think about vertical being up and down, is where the function is going to cross through the vertical or dependent axis. So this is typically the y-axis if we're using x and y. And so the way we determine where the vertical intercept is we look at where the independent variable equals 0, right? When x equals 0, what is the functional value? That's where we cross through the vertical axis, and we call that the vertical intercept. Now you can imagine a lot of scenarios where this would be important. If our independent variable represents time equals 0 is where we start measuring whatever it is we're looking at. So this intercept often becomes very important to us. Similarly, the horizontal intercept is going to be where we cross through the horizontal or independent axis. So this is going to happen when the dependent variable, typically y, equals 0. So when that equals 0, that's where we can cross through the horizontal axis. And again, this will often have important meaning to us when we put these things in context. So what we want to do is we want to be able to look at our function in 4 different ways again. So formula, graph, table, word problem, and determine what our vertical and horizontal intercepts are going to be. Okay, so we're going to start with a formula here. We have x squared minus 2x minus 3. It's our same formula we've been using throughout. But what we want to do now is we want to identify the horizontal and vertical intercept. So again, for the vertical intercept, we're going to let x equal 0 and we're going to solve. And for our horizontal intercept, we need to let y equal 0 and solve. So for the horizontal intercept, there's a little more algebra involved. So I want you to take 2 minutes and see if you can identify the horizontal and vertical intercept for these functions, for this function, and you want to write it as a point, so like x comma y. Okay, so take 2 minutes, see if you can work that out, and then we'll go through it together. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so let's start with the vertical intercept. I'm just going to write VI for vertical intercept. We know that that happens when x equals 0. Since x is our independent variable here, that means we can plug that 0 right in to our function. We get 0 squared minus 2 times 0 minus 3. So we have 0 minus 3. So we get an output of -3. So the way that we write our vertical intercept, actually I'll put it over here, right? The x value comes first and the y value comes second. So when we write our intercepts, we write them as points. And when you write a point, you're going to do x comma y is the general form, but it's the independent value comma the dependent value. So we have a vertical intercept at 0 comma -3. So that's where we cross through the vertical axis. Now to do the horizontal intercept, we have a little more algebra. So I'm going to write this as HI, horizontal intercept. We said that's when y equals 0, right? Or your dependent value is 0. So that means we are setting our function equal to 0. Okay. Now this is a quadratic function. So there's two ways you can solve it at this point. You can use the quadratic equation if you are comfortable with that, or you can try to factor it. It depends on your preference. You'll get the same answer either way. I'm going to factor this one just because I know that it factors nicely. But you, again, if you prefer the quadratic equation, that's totally fine. So again, if you have a quadratic equal to 0, that's when you can use these methods. So again, when you factor, right, we have these coefficients A, B, and C. We're looking for two numbers that multiply to give me C, to give me -3, but add up to give me -2. Okay, and so when we do that, we think of numbers that multiply to give you -3. So -3 and +1 are going to be the factors we're looking for here, because -3 times 1 is -3, but -3 plus 1 gives me the -2. Okay, so those are what's called factors. And I'm sure you've done this before at some point, but this is still just equal to 0. This is just another way to represent our function. And so what factoring does for us is we then get to take each factor and set it equal to 0. So we have x minus 3 equals 0. And that tells me that x equals 3. But I also have x plus 1 equals 0, which tells me that x equals -1. Now, what does that mean here? So since there's two x values that satisfy my equation here, that means that there's two horizontal intercepts. There's one when x equals 3. So 3 comma 0, because remember the y value is going to be 0. But then there's another one when x is -1. So -1 comma 0. So there's two places where our function will cross through the horizontal axis. Now, if I wanted to check this, I could graph it to make sure that I'm getting the same thing. And if you remember, we actually used this function earlier when I drew a graph. I'm gonna throw this back up here for a minute. If you graphed it then, right, you can see that these horizontal intercepts are at -1 and 3, and the vertical intercept is down here at -3. So that matches what we said over here about our intercepts. So if you ever want to check your intercepts, you can certainly use your graphing calculator to make sure that you're getting the same thing. If you get something algebraically and the graph matches, that's pretty good evidence that what you did was correct. Okay, so now let's do the same thing for a graph. Now I recognize that the graphs here are tricky, that you can't see them as much, so I'm just going to walk us through this one. Trace that out. Okay, so when I'm trying to figure out vertical and horizontal intercepts on a graph, I just do them one at a time. So let's start with the vertical intercept. So the vertical intercept, I'm looking for when I cross through that vertical axis. So that happens right here. That's the one place where my function crosses through the vertical axis. So my vertical intercept here is at 0, 0, right? I can see that that's where I cross through. It's right where the two axes meet. Now, you can see here that there's more than one horizontal intercept. And that's pretty common that you have multiple horizontal intercepts. So when I go through, I want to figure out all the places where I'm crossing through the horizontal axis. My tracing wasn't great, but we'll approximate. So I can see here that there's 1, 2, 3, 4, 5 places that I'm crossing through. So the first place way over here, this is -6, and then I'm about halfway. So this is approximately -6.5. So remember, with our horizontal intercepts, the y value is always 0. So that's my first one. My next one is just a little bit to the left of 3. So I'm going to approximate this to be -3.2 on this graph. You may look at it and say, -3.1. That's fine. We're just trying to get the general area. The next one is the one that crosses through right at the origin. So even though that was our vertical intercept, it's also a horizontal intercept because it also crosses through the horizontal axis. And then over here, I'm going to call that +3.2 because it's a tiny bit to the right of 3. And then finally, 6.5, 0. So again, there's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The horizontal intercepts all have a y value of 0. And again, I'm approximating here. If you were going to do this on an exam, it would fall on an integer, or you'd be able to determine very easily from the multiple choice answers. But that's how we identify these on a graph. So we're just literally looking for where we cross through the axes. Okay. So now we have a formula, we have a graph. Next up, we're going to do a table and a word problem. Let's see. Apparently we have 2 word problems today. Okay, so I'm going to have you try these out. So we have a table here, a discrete table. I want you to think about the definition of horizontal and vertical intercepts and see if you can write down what they are. Actually, let's just do the table because we only have 3 minutes left. So take 1 minute to write down the vertical and horizontal intercepts of this table, and then we'll go over it. And then I'll put a pin here. Okay, so take 1 minute, jot down what you think those are going to be. All right, so remember our vertical intercept happens when our independent variable equals 0, right? So when we have a vertical intercept, we're gonna have 0 comma something, okay? So notice here that on our table, we have this value of 0, so we are able to determine the vertical intercept because it's gonna be 0 comma 30. That's the one that's connected to an independent variable of 0. Horizontal intercepts happen when the y value equals 0. So to determine if there's any horizontal intercepts, we want to look in the bottom row and find all the places that we have a 0. So it only happens once here. So we have the 0 here, and so we need to attach it to the independent number input here. And so we have a horizontal intercept here at 6, 0. Okay, so I think it's probably okay if you try the 2 word problems at home, the last 2 problems here. And then if you just read the definition of increasing and decreasing functions, that's the end of 1.1. So you can check those out. There's a video on increasing and decreasing functions on Moodle, but that is all sort of the terminology that we need. And then on Thursday, we'll start off with rates of change, okay? So have a great day and send me an email if you have any questions. I'll see you guys on Thursday.
They can't hear you.
Okay.
Thank you.
Have a good one.